will be equal to y as a function of x is equal to C1 sine Px plus by C2 cos Px. This is our equation 8a now. Okay, so we have that relationship now. Okay, right. So now we have two unknowns. Okay, so what you see over here, right? What you see over here is still our this is known as our general solution. Okay, so we are not done yet. We have to determine, or we have to impose boundary conditions to equation 8a to determine P1 or C1 and what? C2. Okay, so that's where we are going to have our boundary condition. Okay, so in case we forget, okay, some of you might ask me, Eugene, what is small p? So small p, so note that small p is equal to square root of p over ei. Okay, we have done this before. Remember, small p is equal to square root p over ei. Okay, so now we are going to impose boundary condition into equation 8a. Okay, so earlier we have specified some boundary condition over here, right? Remember when we drew the deformation, we wrote down here boundary condition number 1, when x is equal to 0, y is equal to 0. Then when we have boundary condition 2, when x is equal to L0, y is equal to 0. Okay, so let's put in boundary condition number 1. So we're going to substitute x is equal to 0, and then we know that y, the deflection, is equal to 0 into equation 8a. Okay, so from here we know that this is equal to 0 is equal to C1 sine of 0 plus by C2 cos of 0. Sine of 0 will be equal to 0, cos of 0 will be equal to 1. So C2, so therefore from here, C2 is also equal to 0. Okay, so therefore now we are left with y as a function of x is equal to C1 sine Px, and that is our equation 8b because it evolved from equation 8a, and we get rid of cos Px because C2 is equal to 0. Then the next thing that we're going to do, we're going to substitute. So basically, before I go on, I'm into equation number 2. So I will move this if I can. This is from boundary condition number 1. Okay, so we're going to substitute when x is equal to L, y is equal to 0, which is your boundary condition number 2, into equation 8b now. Okay, so equation 8a, boundary condition 8a, boundary condition 1 with x is equal to 0, y is equal to 0. Boundary condition 2, x is equal to L0, y is equal to 0. Okay, so I'll just use the term L. So from here, right, what we have now is this. So when we substitute that, so y at a certain length L, right? So this is equal to C1 sine PL, and the whole term will be equal to 0. Okay. So now we have to we have to step back. Okay, we have to step back. What do you mean the step back? So we have to satisfy this condition. Okay, so we have to think in what condition. Okay, in what sort of condition where C1 sine small p big L is equal to 0. Okay, so we have to think. Okay, so we know we're going to let, the only way is this, we're going to let PL is equal to N multiplied by pi, right? Because sine pi is equal to what? 0. Okay, but before I talk about sine pi, where N is equal, can be equal to 1, 2, 3, 4, so on and so forth. Okay, so if sine pi is equal to what? 0. Sine 2 pi is also equal to 0. Sine 3 pi is equal to 0. Sine 4 pi is equal to 0. Right? So therefore, right? So I'm going to write this. So we know that sine n pi is equal to what? It's equal to 0. Okay. So from here, let me come here. Go on. I'm going to insert a new page. Right. So from here, we know that, I'm going to continue. We know that sine n pi is equal to 0, right? So therefore, small p big L is equal to small n pi. Okay. So from here, we know that small p is equal to n pi over L. Okay. So we remember that small p, note, right? I wrote this again. I'll let you recall. Small p is equal to square root p over big P over EI. Right? So when we put this to the above equation, so this will be equal to square root big P over EI. So this is equal to n pi over L. Okay. So P over EI is equal to n squared pi squared over L squared. Okay. So from here, so therefore, P critical, okay, is equal to n squared pi squared over L squared, and then the whole thing multiplied by EI. So now you can see where the what? Where the pi squared start coming in already. Yes or no? Right, now you can see where the pi squared coming in. So PCR is known as the critical axial load. Okay, critical axial load where buckling will occur. Okay, so now we can also use this formula to calculate our critical stress. So stress to critical is equal to P critical divided by cross-sectional area, right? So this will be equal, or then this will be multiplied by n squared pi squared over L squared EI. Okay. So now note we are going to let n is equal to 1. Why we let n is equal to 1 is because in buckling, you usually get this sort of deformation. Okay, when I say this sort of deformation, which I highlight in yellow, is where n is equal to what? 1. Okay, so now coming back to here, we're going to let n equal to 1. So the entire equation is stress critical is equal to critical load divided by A pi squared over L squared, okay, E multiplied by I. Okay. So interesting feature is this, okay. And again, another note that the second moment of area I is equal to A R squared. Okay, and R is known as the radius of gyration. If you ask me now, Eugene, what is radius of gyration? I'll be honest with you. I have not a clue now. Okay. What does it actually mean physically? I also don't know. Okay. But we know that based on this formula over here, R is equal to square root I over A. That's all I know. Okay. So therefore, R squared is equal to I over A. Okay. So we know that we have a in the denominator here. Let me use a different, let me use a highlighter. We know we have a in the denominator. We know that we have a I in the numerator. So we can substitute R squared into that equation over there. Okay, so therefore, the critical load will be equal to uh sorry, I think I mess up somewhere over here. This should be equal. I do apologize. Okay, I do apologize. Let me rewrite this. Okay, so PCR over A is equal to n squared pi squared over L squared, the whole thing bracket E I over A. Okay. So when I rewrite this out, okay, so we have a I over here, or I'm going to highlight over here. We have a I over here, we have an area over here. Okay, so we know that the critical squares is equal to n squared, right? N squared pi squared over L squared, and then we have E R squared. And then we are, as I said earlier, we're going to let n is equal to 1. We have pi squared over L squared E R squared. And we will usually write the critical stress is equal to pi squared E over L squared over R squared. Okay. And the last step before I stop, we rearrange this as pi squared E over L over R squared. Okay, and L over R is commonly known as the slenderness ratio. Okay, I'm going to stop here. Okay, next week we are going to start on still centric buckling, and I'm going to do some examples. I'm going to post homework tomorrow. Okay, and the due date will be not this coming Tuesday, next Tuesday. I make sure you have like 7 days for your homework. Okay, if that's the case, thank you for your time. I'll see you all next week. Have a good weekend.